Okay, simultaneous requirements to reference the datum features of size. So here's an example. We have a cylindrical part with a bore going down this axis of the cylinder, and then we have a notch in the base, and then we have two holes going through the part at opposite axes, 90 degrees. They reference the same datums, but they're in different orders, so that means they're different reference frames. And we've got maximum material condition called and maximum material boundary. So what we have below is a fixture that would be used, the functional gauge would be used to check this. You have a cylinder with a base and a notch feature that would go into our part. So this whole thing would slide into the end, and then you have two gauge pins that would need to slide through their respective holes and smoothly go in, and it locks in place. The maximum material boundary defines how big that notch feature on the tool is. So we have maximum material condition on datum C, and you can see that that simulator is made at 240 thousandths thick, tolerance, which is 2 thousandths, and because it's at maximum material condition, allowance, you subtract another 8 thousandths. So the simulator is made at 240 thousandths because that's going to accommodate the part that slides on there at maximum material condition, which would be the smallest that feature is allowed to be. Then that notch locates on the part. Pin size is based off maximum material condition. So the hole call out is 328, and we're going to subtract. So if the hole is at maximum material condition at a -0 hole size, that would be 328, and then we would subtract 16 from it. So identical datum feature references create one pattern. The position and relationship between the features with the position tolerances are at their basic dimensions on one TZF. So you can use the same gauge for both sets. Now here is an example of the same part, except for they've explicitly labeled separate requirements. So you can't, the simultaneous requirements are the default for the first segment, and a group of features may be specified to allow the TZFs to move separately despite identical datum features. So that allows those two holes to deviate from each other. And so it's notations required under the feature control frames for that to apply. And the two position tolerances are specified as separate requirements, and two functional tools are used to verify the requirements. So the first functional gauge would look like this, still locates on the notch at the same width because of the maximum material boundary, but it's only used to check the lowest hole. Then separate requirements are for the lower segment, which are going to use a second functional gauge that looks very similar, but it can only check that one hole feature. So, and they have to be calibrated, and the functional gauges have to be super precise. So, so there's an example of interpretation of that call out. Now in practice, I don't think I've ever seen SEP or REQT. I don't know if I've ever seen that. So it might be industry specific, but for the most cases, it's usually the first scenario we showed on the previous slide. Okay, default simulators for separate requirements for composite tolerances. So simultaneous requirements by default for the first segment. One functional gauge can be used. Separate requirements default to the lower segment, and two functional gauges required. So just like the previous example, you'd have to check each pattern independent to each other. You could really use the same fixture. You would just have to have the pins are removable so that you're only checking one of these two patterns at a time. Okay, noted simultaneity requirement for composite position tolerances. So the functional requirements may need holes of different sizes that act as a single pattern. Notation must follow underneath the callout simultaneous requirement, or SIM. REQT is an abbreviation. One functional gauge. So here's a coaxial hole pattern. We have 3 holes, they're different size. They often require close position relationship to one another. The pattern may have a large location tolerance, and the holes may have different diameters. So the way this is interpreted is the first line is need a combined coaxial tolerance on the first line, and then individually to each other, I believe they have to be the tighter of the two tolerances. Coaxial hole patterns locating and feature relating tolerances. So here's another example. The first frame pattern is the locating tolerance. So it's going to locate the zone, constrain the translation and rotation to the datum reference frame. And the pattern has a locating zone, and it's the same on both holes. And it specifies the pattern location and to the pattern tolerance zone framework. Now the second frame refers to them independently of each other. So the tolerance zone framework constrain the rotation only to datum A, primary, and datum B in the secondary. And so you have a tighter tolerance for the whole, but less on the rotational tolerance. Okay, other coaxial tolerances. 2 or more coaxial features tolerance relative to another. So here we have a workpiece and a gauge that's set up to check the position tolerance of this, I think, round part into a gauge. And again, the gauge is going to be sized at maximum material condition if it has the modifier there. One coaxial feature identified as a datum feature, others applied position tolerance for referencing identified datum. So since datum A has maximum material boundary, it's made at maximum material condition, and the size of the other feature is made at the virtual condition feature size. So since it's an external feature, the maximum material condition size is 0.567 plus 5 thousandths, which gives us 572 thousandths. And that plus 5 is coming from the tolerance with the maximum material condition call out. And a position tolerance is typically applied at MMC when the assembly is the main concern. Radial hole patterns. Axis passes through the center of a circular shape. The TZF centered on a perpendicular or primary datum axis. Holes may move independently within their tolerance zones. Symmetrical position. Symmetry is a condition where features on each side of the center line or center plane are equal. Position and profile tolerances specify location, accuracy requirements, and the feature control frame formatted is same as position tolerance specification. So here's a position for symmetry of a hole pattern. The datum feature identified that it creates an axis or plane of symmetry. And that is because of the location of the datums are aligned with the actual dimension. So what we're creating is virtual symmetry with it. The positions tolerance relative to the datums applied to the express require control. And the TZF pattern for the holes locates symmetrically relative to the reference datums. And no dimension from the center plane is required for this to apply. It has to do with the configuration of the datum C and B being lined up with the dimension implies it's centered. So you don't have to actually have the center marks. Okay, past practices. These are symbols not used in ASME Y14.5-2018, but they eliminated symmetry prior to 2018. So there used to be this symmetry symbol that was used. Now it's the relationship of the datum with the dimension line instead. And concentricity was eliminated before 2009 version. So it's the use of position tolerances made both of these obsolete with the new interpretations. It's better definition of requirements, achievable without other tolerance characteristics. So that's what they determined. So these became redundant symbols. You still see them on old drawings though. And drawings based on previous standards may include these symbols, and if they call out that previous standard, that's what you have to hold the drawing to, is interpreting it to that version. In summary, as functional requirements become more complex, so does the need for precise and clearly defined tolerancing strategies. In this lesson, you learned how to apply functional gauge techniques to verify hole positions specified at maximum material condition, or MMC, and how to construct and interpret composite position feature control frames. We also examined how to use the identical datum feature references across multiple position specifications and can impact design intent and inspection. Additional topics include specifying separate pattern requirements for feature groups, tolerancing inline holes, and using position controls to manage symmetry and coaxial features. This lesson equipped you to apply these expanded principles to complex part designs with confidence and clarity. In conclusion, by the end of this lesson, you are able to explain functional gauging concepts for checking hole position tolerances specified at maximum material condition, specify and explain composite position feature control frames, explain the effects of using identical datum feature references in multiple position tolerance specifications, specify separate pattern requirements for groups of features not acting as a single pattern, specify position tolerances for inline holes, and specify position tolerances to control symmetry, and specify position tolerances to control coaxial features. This concludes this lecture, and thank you for sitting through it, and I hope you got something from it, and we'll catch you on the next one.